Have you ever wondered where everything began? The stars, the planets, even time itself? It all started 13.8 billion years ago with one incredible event, the Big Bang. But here's the twist. It wasn't a literal explosion. Instead, it was the start of something even more extraordinary. In today's video, we're going to unravel the mysteries of the Big Bang, the birth of the universe. And by the end, you'll see how this one moment in time created everything we know and everything we still don't. Let's clear up a common misconception. The Big Bang was not an explosion, but an expansion, an event marking the birth of our universe around 13.8 billion years ago. It began as a singularity, a point of infinite density and temperature, where all the matter and energy in the universe were concentrated. In a fraction of a second, this singularity expanded rapidly, creating space, time, and the building blocks of everything we know today. This expansion continues even now, with galaxies moving farther apart. The Big Bang theory is supported by evidence like the cosmic microwave background radiation, the expanding universe observed by Edwin Hubble, and the abundance of light elements like hydrogen and helium. In short, the Big Bang was the moment that started the universe's journey from an unimaginably tiny, hot, and dense state. But the main question is, what existed before the Big Bang? This question not only challenges our understanding of the universe, but also pushes the boundaries of human thought. According to Albert Einstein's theory of general relativity, time didn't exist before the Big Bang. This means the idea of a before might not even make sense. It's a concept that defies our everyday experience of time. One of the most intriguing theories about what came before the Big Bang is called eternal inflation. Imagine the universe as part of a vast, ever-expanding cosmic field. This field, known as the inflationary field, might have existed long before our universe. According to this idea, our universe is just one bubble in a vast multiverse, with countless other bubbles forming and disappearing. The Big Bang, in this scenario, wasn't the beginning of everything, but just the start of our bubble's existence. This theory hints that there might be infinite universes, each with its own unique properties and laws of physics. Another fascinating hypothesis is the cyclic universe theory. What if the universe is like a cosmic phoenix, rising from its ashes over and over again? According to this theory, the universe goes through infinite cycles of expansion, like the Big Bang, and contraction, a big crunch. After each contraction, a new universe is born. This theory suggests that the Big Bang wasn't a one-time event, but part of an eternal loop of creation and destruction. It's a poetic idea that connects us to a much larger cosmic rhythm. In the realm of quantum physics, things become even more mysterious. Some scientists believe that before the Big Bang, there was a quantum vacuum, a state of pure potential, with no matter, no energy, and no time. Tiny quantum fluctuations in this vacuum could have sparked the Big Bang, creating our universe out of seemingly nothing. This concept challenges the very notion of nothingness, suggesting that even in the absence of matter, there's still a sea of potential energy waiting to burst forth. Despite these theories, the truth about what existed before the Big Bang remains elusive. Our current understanding of physics breaks down when we try to look beyond that moment of creation. The singularity at the heart of the Big Bang is a place where our laws of nature no longer apply. It's a boundary that science is still struggling to cross. Now you might be wondering, how do we know the Big Bang even happened? Great question. Let's explore the compelling evidence that supports this groundbreaking theory. 1. The expanding universe. In the 1920s, astronomer Edwin Hubble made a monumental discovery that transformed our understanding of the cosmos. By observing distant galaxies, he noticed a remarkable phenomenon. These galaxies are moving away from us, and crucially, the farther away they are, the faster they're receding. This observation led to the formulation of Hubble's law, providing strong evidence that the universe is expanding. If we imagine rewinding this cosmic expansion, it suggests that everything converges back to a single, infinitely dense point, a concept that aligns perfectly with the Big Bang theory. 2. the cosmic microwave background. Fast forward to 1965, when scientists Arno Penzias and Robert Wilson stumbled upon a faint microwave radiation permeating the entire sky. This wasn't just random noise, it was the cosmic microwave background, or CMB, essentially the afterglow of the Big Bang. This ancient light is a snapshot of the infant universe, providing a direct link to its origins. The uniformity and spectrum of the CMB have been studied extensively, offering a wealth of information about the early universe's conditions and further corroborating the Big Bang model. 3. The abundance of light elements. Another compelling piece of evidence lies in the cosmic abundance of light elements, particularly hydrogen and helium. According to the Big Bang nucleosynthesis theory, these elements were forged in the intense heat of the universe's first few minutes. Observations reveal that approximately 75% of the universe's normal matter is hydrogen. About 25% is helium, with trace amounts of deuterium and lithium. These proportions align remarkably well with theoretical predictions, reinforcing the Big Bang model. The presence of these light elements in such specific ratios is difficult to explain without invoking the conditions present during the universe's earliest moments. These three pillars, the expanding universe, the cosmic microwave background, and the abundance of light elements, form a robust foundation of evidence supporting the Big Bang theory. Together, they paint a compelling picture of our universe's fiery origins and its ongoing evolution. What happened after the Big Bang? Ever wondered how the universe evolved after the Big Bang? Let's continue our journey through the cosmic epochs that shaped everything we know today. Immediately after the Big Bang, the universe was in the Planck epoch, a period so extreme that our current understanding of physics breaks down. All fundamental forces, gravity, electromagnetism, and nuclear forces, were unified, and the universe was unimaginably hot and dense. As the universe expanded and cooled, it transitioned into the grand unification epoch. Gravity separated from the other fundamental forces, which remained unified as the electronuclear force. This era set the stage for the subsequent separation of forces that would govern the interactions of matter and energy. During the inflationary epoch, the universe experienced an exponential expansion, growing from subatomic scales to macroscopic sizes in a fraction of a second. This rapid inflation smoothed out initial irregularities, leading to the large-scale uniformity observed in the cosmos today. It also stretched quantum fluctuations, seeding the formation of galaxies and large-scale structures. In this epoch, the strong nuclear force separated from the electroweak force, leaving electromagnetism and the weak nuclear force unified. Particle interactions were highly energetic, leading to the production of W and Z bosons and Higgs bosons. The Higgs field became active, imparting mass to particles through the Higgs mechanism, a fundamental process in particle physics. As the universe continued to cool, it entered the quark epoch. Quarks, the fundamental constituents of protons and neutrons and gluons, the carriers of the strong force, formed a dense, hot plasma. The temperature was still too high for quarks to bind together into hadrons, so they existed freely in this quark-gluon plasma state. Cooling further, the universe reached temperatures that allowed quarks to combine, forming hadrons such as protons and neutrons. This transition marked the end of the quark-gluon plasma state and set the stage for the formation of atomic nuclei. During the lepton epoch, leptons, particles like electrons and neutrinos, dominated the universe. The majority of hadrons and antihadrons annihilated each other, leaving behind a small excess of hadrons that would form ordinary matter. Leptons and antileptons underwent similar annihilation processes, with a slight excess of leptons remaining. In this era, the universe was filled with a hot, dense plasma of nuclei, electrons, and photons. Photons were constantly scattered by free electrons, preventing light from traveling long distances. This foggy state persisted until the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. Approximately 380,000 years after the Big Bang, the universe cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms, in a process known as recombination. This led to the decoupling of matter and radiation, allowing photons to travel freely. These photons constitute the cosmic microwave background, a faint glow observable today that provides a snapshot of the early universe. Following recombination, the universe entered a period known as the Dark Ages. With no stars or galaxies yet formed, the universe was devoid of visible light. However, slight density fluctuations existed, which would eventually lead to the formation of cosmic structures. Over time, regions of higher density began to collapse under gravity, leading to the formation of the first stars around 150 million years after the Big Bang. These population 3 stars were massive and short-lived, producing heavy elements through nucleosynthesis. Their formation ended the Dark Ages, initiating the epoch of reionization, where ultraviolet light from these stars ionized surrounding hydrogen. Galaxies formed as gravitationally bound systems of stars, gas, and dark matter, becoming the building blocks of the large-scale structure of the universe. Approximately 4.6 billion years ago, or 9.2 billion years after the Big Bang, our solar system began to form from a collapsing cloud of gas and dust within the Milky Way galaxy. The central region formed the Sun, while the surrounding material coalesced into planets, moons, and other solar system bodies. About 3.8 billion years ago, simple life forms emerged on Earth. Through the process of evolution, life diversified and became more complex, coming to next point, role of dark matter and dark energy. But there's more to the story. Most of the universe is made of stuff we can't see, dark matter and dark energy. Dark matter acts like an invisible glue, holding galaxies together. Meanwhile, dark energy drives the universe's accelerated expansion. It's wild to think that 95% of the universe is made of things we don't fully understand. It's a cosmic puzzle waiting to be solved. So, what's next for the universe? Scientists have proposed several theories. 1. The Big Freeze. The universe keeps expanding until all stars burn out. 2. The Big Crunch. Expansion stops and the universe collapses back into a singularity. 3. The Big Rip. The expansion becomes so extreme that it tears apart galaxies, stars, and even atoms. Whichever fate awaits us, one thing's certain: the story of the universe is far from over. So, what do you think? Does the Big Bang Theory change how you see the universe? Let me know your thoughts in the comments below. And if you enjoyed this journey, don't forget to like, share, and subscribe for more incredible content. Thanks for watching, and I'll see you in the next video.